Hi all, this is Naren from Shastra Deemed University, Tanjore. This is a video in continuation of the unit for fixed and fluidized bed. In this video, we will focus on fluidized bed system. I'll give you an introduction of the topic on fluidized beds. This is part of the fluid mechanics course for the Beta Chemical Engineer second year. Now let's start our discussion with just fixed bed, and then let's go through the fluidized bed. Now I hope you are fairly thorough with what a typical fixed bed look like. I have given a schematic sketch here. You have a bed which is filled with particles, and the fluid is flowing through the bed. This can be upflow as shown in the diagram, or it can also be a downflow system where the fluid comes from the tops and goes down, and this can also be an horizontal system. So this fluid actually goes through the spaces between these particles, uh, and these particles, how are they kept in place? So that means what keeps them by not falling down or going carried away by the fluid. So that's for that we have a distributor plate or a support plate system. So in a fixed bed there is a distributor plate or a support plate at both the ends of the bed. So you also have at the upstream end from where the fluid enters the bed, and you also have at the downstream end where the fluid leaves the bed. So there is a distributor or a support plate at both the ends, and this ensures that the particles are not carried away by the fluid. Now let us assume that you have two pressure tappings. Now let's take the case of an upflow system, and you have two pressure tappings P1, P2, and time being, let us focus only on the frictional pressure drop between P1 and P2. We will not account for the static head. So what I mean by the static head is the HRG component between P1 and P2. So if I ask you the question, suppose on a plot, if we plot this pressure drop, this frictional pressure drop between P and P2 at a different flow rate, what is given is Q here is the volumetric flow rate. It could be volumetric flow rate or mass flow rate or the superficial velocity. Suppose if I plot pressure drop versus superficial velocity, can you just tell me how this plot will look like? Uh, Before you can just take a minute to see how this plot looks like. You can. The hint is think of an ergon equation and see where is this term in the ergon equation, and where is the flow rate term in the ergon equation, and then think where is how this plot should look like. Now if you have taken your ergon equation, and this is how something that you should have arrived at. So this plot fairly looks like a straight line at very low values of flow rate, and then afterwards it is expected to curve. This frictional pressure drop, remember I'm only plotting the frictional pressure drop and not the static bed pressure drop. So this frictional pressure drop at very low values of velocity, so that means we have low flow rates, low velocity. When you have low flow rates, only the viscous term dominates, because the inertial term is square of the velocity, so which may not be appreciable enough. So that means this will look like a straight line, because pressure drop will be proportional to velocity there and the flow rate there. In this region B, when the velocity is very high, so that means this will curve. Okay, so that means you will have a quadratic expression. Now in this expression, or in this experiment on fixed bed, let's do one thing. Suppose if I remove these two support plates, what do you expect? So what if the distributor plates are removed? Suppose if you just have a bed of particles and there are no beds here, there's no bed here, what do you expect then? Uh, so do you think like we can remove both the plates? No, obviously I don't think we would be able to remove both the plates, at least in this diagram upflow bed that is shown. If I remove this plate, everything will fall away. So that means I am assuming that we will be able to remove only the top plate. Probably I can remove the bottom, I need not remove. So let us assume that we are removing only the top plate, and we still have the bottom plate. So as per the diagram shown here, so there is again a bed filled with particles. You can see the fluid is flowing through the spaces. You still have the pressure trappings. Only the bottom plate is there, the top plate is not there. Now if the bed is like this, and now you want to plot on the same plot how pressure drop looks like flow rate, what would be your answer? Do you expect the same behavior like this, or you expect anything else? So you can think of for a while, and then let's populate, let's jot down what are the different things that we can expect. You can pause and think the video if you want. Now I'm sure that some people would have said the particles will fly away, will get carried with the fluid stream. Some will say the bed will get emptied of solid particles, all this will go off. Some might even say that the particles will start mixing among themselves because now they are not held up between the plates. Now what do you mean by particles start moving? So that means you mean moving out of this, or just moving here and there? That also you should think. And somebody might say that nothing will happen, the bed will remain the same, or that means the plot will remain the same, right? So I'm not going to say all these are correct, I'm not going to say which of these are correct, but all I would expect that it is something of this sort you should have thought. So I again repeat the question. The thought process is, you have a bed, you have only the top plate, you don't have the you have only the bottom plate, you don't have the top plate. You are allowing the fluid to flow through this bed, and you are slowly increasing the flow rate of the fluid through this bed and trying to measure what is the pressure drop. So I'm asking what happens to the pressure drop through the flow rate and in this system. Well, if you are not able to imagine, you need not worry. You can stop the video here, and I would request you to see this YouTube video. Let me just show that YouTube video to you. So you can note down this URL which you now see on the screen. I will also put this on the Google Classroom. This is fairly just a 1-minute video, so you can just see what happens if you have particles, and so it's filling up with glass beads of 500 to 600 microns, which is 0.5 mm to 0.6 mm, and then if you send without the top plate, what happens? So you can look into this video, right? He is trying to show something by height and everything, and then we can come back. All right. Okay, let's me go back to the file. So let me assume that you will see through that video. So what was experimentally observed was rather something like this. So when the pressure drop was plotted against a flow rate or the superficial velocity, remember the superficial velocity is based on the empty cross-sectional area of the bed. So what I mean by the empty cross-sectional area of the bed is this area. So this area, okay. It was found that at very low flow rates, at very low velocity, this was almost a straight line passing through origin, and after some point, so this point which I have marked here, the pressure drop becomes almost flat. So that means the pressure drop did not vary. So this is very interesting, right? More, we typically know that more the fluid we pump in, more the flow rate is more the fluid we pump in, more the fluid we pump in, more should be the pressure drop, because you know that pressure drop is directly proportional to velocity. So more the fluid you pump, more should be the pressure drop. But something contrast different happens here, that pressure drop do increases in the region A, but in the region B, what you see is the pressure drop is almost constant. Pressure drop is fairly constant, it does not changes. Along with this observation, what experimentally something else is also observed is what shown here, the height of the bed. Now what I mean by the height of the bed is this distance, the distance from the distributor plate to the top surface until which the particle is there. Now this is a free space where there is no particle, so I will only consider this height. This height of the bed is constant till some part, so that means corresponding to this region A is this is constant, and after this transition point this bed height keeps on increasing. So this is what is observation. This is what one can also see experimentally. I think we might have not noticed this pressure drop in the YouTube video which I have shown, or which the URL which I have shown, but probably you would have noticed that this bed height increases with respect to the flow rate. So this critical point, this transition point, which actually differentiates this region A and B, is called the incipient fluidization point, or the point of minimum fluidization. This region A is actually the fixed bed and the region B is actually the fluidized bed. So that means when your operating flow rate or the velocity is less than this transition, the bed is said to be fixed bed. When your operating flow rate or the velocity is more than this critical velocity, more than this transition velocity, that means which is in this region, then it is going to be a fluidized bed. This point is called the minimum fluidization velocity. That means at this point I would like to pause and maybe give you some exercises to think. Why is this bed beyond this point is called fluidized? So we know why it is called fixed. So when we say it is fixed, so that means the particles are not moving. Now why this region is called a fluidized bed? So that means why the term fluid is being used. What is the different features that is observed in a fluidized bed compared to a fixed bed? So for this I would like to take up this during our online interaction, and I would also request you to go back and see this book on McCabe and Smith to try to find answers to these questions or this thought process. You can see even the YouTube links that I have posted in the Google Classroom. So I once again repeat, I want you to think, why is this region called a fluidized bed? That means how far is this region different from this region? So that means above this transition point, once the operating velocity or the flow rate is beyond this transition point or minimum fluidization point, then what features does the bed exhibit? This is what is the thought process for you to find out. And the follow-up is once we know that there is some transition happening, so that means there is one transition happening, the obvious question of an engineer is, can I predict this transition point? So that means for a given particle fluid system, without doing experiment, so without doing experiment and getting this curve, is it possible to estimate this minimum fluidization velocity? So that's the second question. So that means given the fluid system or the particle system, so can we estimate this point of minimum fluidization where the bed transition happens from fixed bed to a fluidized bed, right? So it is possible. We will see this as a part of the second video on the same topic. I'll just stop here. So what we have seen so far in this video is how the pressure drop versus flow rate or the velocity happens in a fixed bed. And so that means in a fixed bed means where you have both the distributor plates, how this plot looks like, and what if the top plate is removed, how this plot looks like. And we identified that there is a transition regime happening. So you have a fixed bed regime and you have a fluidized bed regime, and this transition flow rate or the transition velocity is called minimum fluidization velocity, and the flow rate corresponding to the minimum fluidization velocity. I've given you a short exercises on finding out the different flow features or the characteristics of the fluidized bed, and the task is, given the fluidized bed and a particle system, is it possible to estimate, calculate without doing experiments this point of minimum fluidization? Thank you here, and I'll meet you in the second part of this video. Thank you.